Hi everyone, here is the challenge example. So we have been working on the example 3x3 matrix. We saw the distinct real roots and the repeated real root case. We haven't seen the complex root case. So this challenge example is going to be the complex roots. Okay, so let's see why it's hard. Okay, let's see. So A, this is our A. And then we compute the characteristic equation, which is the determinants of A minus lambda I. Okay, so we subtract lambda from the diagonal element. And then minus 1, all the other entries stays there. Okay, so here, let's multiply let's calculate the determinant. Let's use the first row. Then this is plus, this is minus, this is plus. Okay, so this is negative 2 minus lambda times the determinant of the submatrix minus 1 minus lambda 1, negative 3, 4 minus lambda. And then minus negative 2. Minus 1, 1, minus 3, 4, minus lambda. And then plus negative 9. Then we have minus 1, 1, minus lambda, 1 and 1. Okay, let's continue. So this is minus 2 minus lambda of 1 minus lambda, 4 minus lambda, minus 3... minus negative 3, so plus 3 times 1, okay? Negative become positive. 2 times minus 1 times 4 minus lambda minus negative 3, so plus 3. Minus 9, and then we have minus 1 times 1 minus 1, minus 1 minus lambda. Okay, minus 2 minus lambda. And what's this guy? So 4... minus lambda minus 4 lambda plus lambda squared plus 3. Here's minus 4 plus lambda plus 3. Here is minus 1 plus lambda. Okay, let's continue. Yeah, a lot of algebra, yes. So we order it. So lambda squared minus 5 lambda plus 7. Here we have 2 times lambda and 3 minus 4 is minus 1. Minus 1 times 2, minus 2. And here, minus 9 times negative 2 is plus 18. Minus 9 lambda. Okay? Yes. See, I'm already skipping a little bit steps doing the calculation because this problem is going to be so long. Okay, so distribute it. Minus 2 times lambda squared is minus 2 lambda squared. Minus 2 times minus 5 lambda is plus 10 lambda. And then minus 2 times 7, negative 14. Minus lambda cube, minus plus 5 lambda squared. Minus 7 lambda. Okay, and then we can combine these, become minus 7 lambda, and combine this, become plus 16. Okay, almost. Let's reorder it. So minus lambda cube, and then how many lambda square? We have minus 2 lambda square and then 5 lambda square. They give us 3 lambda square. How many lambda? 10 and 7, so 10 minus 14 is minus 4 lambda. And what's the constant? The constant is negative 4 plus 16, so plus 2. Okay, so we set this guy equal to 0. We like the leading coefficient to be positive, so let's multiply by minus 1. Then we flip all the sign. So far, so good, everybody? Okay, so when we get to this step, what's the next step? Well, rational root theorem. Rational root theorem let's look at the factors of the constant term, which is -2. That's plus or minus 1, plus or minus 2. And what other factors of 1? The leading coefficient is 1, plus or minus 1. So the possible roots are plus or minus 1 and plus minus 2. Okay, so let's try those roots. We try our lambda equals to 1. P of 1 is, okay, so what's P of 1? Let's plug in it. 1 minus 3 plus 4 minus 2. What is that? 2 minus, so that's minus 2 plus 2. Oh, we're so lucky. We get the first one. So lambda equals to 1 is a root. Then lambda minus 1 is a factor. Okay, good. Because we have degree 3 is enough to find one root, because then we can use the long division to find the remaining quadratic factor. Okay, so what is that? So we have lambda squared, then lambda cubed minus lambda squared, minus 3 lambda squared plus lambda squared is -2 lambda squared. Right, we use the first line, subtract the second line. Negative become positive. And then minus 2 lambda squared plus 2 lambda. 4 lambda minus 2 lambda is 2 lambda minus 2. Oh, so it's plus 2, right? Then it's 2 lambda minus 2 is 0. Okay, so P of lambda equals to lambda minus 1 and lambda squared minus 2 lambda plus 2. All right, let's see here. So the first root lambda is 1. Well, this guy, can we factor it? Not quite. So let's use the quadratic formula. 2a, a is 1, negative b plus or minus b squared minus 4ac. Wow, 4 minus 8 is -4, so 2 plus or minus 2i over 2. Well, that's 1 plus or minus I. So we have 2 complex roots. So the total, you can see, the total we have 3 roots because it's a degree of 3 polynomial. We're supposed to get 3 roots counting multiplicity. Okay, so let's look at each root. So first, when lambda equals to 1, let v be x, y, z. A minus lambda I times 3 is 0. Okay, what is A? Okay, that is A. Okay, I just copied the A here. So A minus lambda I is, let me use a different color. Okay, so A minus lambda I, we minus 1 on the diagonal elements. Minus 2 minus 1 is minus 3. 1 minus 1, 0. 4 minus 1, 3. Okay, let's see. Whoa, let's swap row 1 and row 2, okay? Then we get minus 1, 0, -3, 0. Then -3, -2, 9, 0. Sorry, -9, 1, 1, 3, 0. Okay, so now we can see we can use -3r1 add to row 2 and row 1 add to row 3. Then minus 1, 0, -3, 0. We have so we get 3 plus 3, 0. And then 0 plus -2, -2. And then, oh, Negative 3 times negative 3, 9. 9 minus 9, 0. Okay, and then next one we have 1 plus 1, 0. 1, 3 plus 3, negative 3, 0. Okay. You can see the second row is a multiple of the third row. So we get minus 1, 0, minus 3, 0, 0, 1, 0, 0. So what we're doing, we can divide it by 2 on R2, and then we can minus R2 plus R3. Okay, so here we have like 2 steps. Okay, so we have an action form. This is x, y, z, right-hand side. Second row tells us that y equals to 0. First row tells us minus x minus 3z is 0. So x is negative 3z. Okay, so v is negative 3z, 0z. Oh, negative 3, 0, 1z. Okay, so you can pick z equals to 1. Then you get v, which is negative 3, 0, 1 is an eigenvector. Okay, so because we have 3 eigenvalues, each eigenvalue we're supposed to get 1 eigenvector. Okay, together, let's continue. Let's use a different color. Okay, let's continue. So 1 plus minus I. So let's do 1 plus I. Okay, so what is a minus lambda I? Well, a minus lambda I is negative 2 minus 1 minus I. So negative 3 minus I. Then negative 2 and negative 9 there. Minus 1, 1 minus 1 minus I. So minus I. 1, 1, 4 minus 1, 3, and minus I. Okay. Well, you can see the 1,1ng, we can swap row 1 and row 2. Let's swap row 1 and row 2. Minus 9, 0, 1, 1, 3 minus I, 0. Okay. All right, let's see. So we get, we want to use the first entry to kill the entry below it. How do we do that? So we can do, negative times, so let me see, 3 plus I, okay, multiplied by negative 1, R1, add to row 2, and row 1 add to row 3. Okay, so minus 1, minus I, minus 3, 0. Okay, so the 1 to entry minus 1 times that become 3 plus I minus 3 minus I. This is 0. And then this guy. Okay. So you can do it on a scratch paper like me. Okay. So this entry we use minus I times negative become positive 3 plus I minus 2, right? So it's 3I plus I squared. I squared is minus 1, minus 2. So 3I minus 3. This is so ugly. Okay, so let's continue. This entry, we use negative 3 times negative 3 plus I minus 9, right? So negative become positive, so it's 9 plus 3I minus 9. So they cancel, we get 3I here. Okay? So, and then this is 0. Okay, next one. 1 minus 1, 0. 1 minus I here. And then 3 minus 3 cancel, so we have minus I. So far, so good, everybody? Oh, now can you see what happened? So we can divide it by 3 in the row 2. Then we have I minus 1 and I 0. Can you see now is the negative of row 3? So we can do this row 2 add to row 3, then we get all cancel out and get 0. So here I'm also combining two sets in one set, because this problem is long, so sometimes if the sets are easy, then we can combine them together. Otherwise it would take patience. Okay, x, y, z on the right hand side. You can see that all of the last row is zeros. Okay, that's always the case. So I minus 1y plus iz equals to 0. So y is iz over I minus 1. Okay, so when we work with complex numbers, we don't want to see complex number I in the denominator. Okay, it's like you rationalize it. Okay, so how do we get rid of the complex number, the imaginary parts in the denominator? Well, you multiply by its conjugate. Well, the conjugate for I minus 1 is I plus 1. It's the same thing, but you change the sign in the middle, right? Then now we have I plus 1, z. Let's put the z out, okay? Let's work with the coefficient of z. So I minus 1, I plus 1 is then I squared minus 1. I squared is negative 1, so that's why we get I plus 1 over negative 2, z. And we distributed I squared is minus 1. And then we have the I there, negative 2. So the answer is 1 minus I over 2z. So far, so good, everybody? Okay, let's plug in the first row. So minus x minus iy minus 3z equal to 0. So x is, I'll move the x to the other side, minus iy minus 3z. Okay, minus iy, minus I times 1 minus I over 2z minus 3z. Okay, what is this guy? Oh, so that's still x. Okay. Oh, where is it? Oh, I need more space. Ah. Okay, let me see. How can I get more space? Okay, here we have more space. So x is, let's distribute it. So minus 1/2 I, and then minus I times minus I is positive I squared. Positive I squared is negative 1. So minus 1 over 2z. Minus 3z is minus 1/2 I. Sorry, I, there's also z there. Okay. Minus 3z. So, sorry, 1 minus 1/2 minus 3 combined together is 7 over 2. So this is minus 1/2 I minus 7 over 2z. Okay. So let's see. Okay, hi everyone. I realized I have a small mistake. So here when we solve for y is minus iz over I minus 1. So there is a minus here. And then so there's minus here, there's minus here, then minus plus, and this is minus, this is plus. Okay, so this is minus, this is plus, then this is plus. and this is plus. So we have this is plus, and 1/2 minus 5 is negative 5. So, 1/2 minus 6/2 is negative 5/2. So the answer is 1/2 minus 5/2 z. Yeah, so sometimes we have to be very, very careful. A minus sign can actually yes. Okay. So what is v then? V is x is 1/2 I minus 5/2 z. I can factor the z out. Y is minus 1/2 plus 1/2 I z and z. So we can pick z to be 2 to get rid of the fractions. So v is then multiply by 2, then I minus 5. And that one is minus 1 plus I, and then z is 2. Okay, so this is our eigenvector. Okay, so we can see the eigenvalues, they appear as pairs. So the eigenvector, they also appear as complex conjugates. Okay, so let's do the other one. So the other one is lambda equals to 1 minus I. Okay, let me change different color. 1 minus I. Okay, so what's the matrix again? So the oops. Okay, so I moved my A right here. So A minus lambda I is negative 2 minus 1. So negative 3 minus become plus I. Negative 2, negative 9, 0. And then 1 minus 1 is 0. Minus negative I is I. And then we have 1. 4 minus 1 is 3. Minus become positive I. Okay, so let's swap row 1 and row 2. Or how about, yes, let's swap row 1 and row 2. Okay, so what do we get? Negative 1, I, negative 3, 0, negative 3 plus I, negative 2, negative 9, 0. 1, 1, 3 plus I, 0. Okay, and then use the 1, 1 entry to kill the entries below it. So how can we do that? We use the minus 1. So we use like 3. We use negative 3 plus I times row 1 add to row 2, right? Then we can kill it. And we use row 1 add to row 3. Minus 1, I, negative 3, and 0. Let's leave more space here. Okay. Alright, scratch paper. Ready? So this guy is 0, right? So because we subtract the same thing is 0. So this guy is negative 3 plus I times I minus 2. So it becomes minus 3I. I squared is minus 1 minus 2. So it's negative 3I minus 3. So far so good. So I hope that in this example you can also learn how to work with complex numbers. Okay, so how about this guy? Negative 3 times negative 3 plus I minus 9. So that's 9 minus 3I minus 9. 9 cancel. Negative 3I. So far so good, everybody? Okay, and then this is 0, and then we have 1 minus 1 is 0, 1 plus I, 3 minus 3 cancel I. Okay, so you can see common factor divided by -3 in second row. We will get minus 1 I minus 3, 0. 0, and then I minus 1, I, 0. Sorry, divided by -3 become I plus 1. Oh, and then you can see, wow, it's the same as the last row. So we can use minus row 2 add to row 3 in the next step. Then we get zeros in the last rows. Okay, that's always the case. We need to see the last row contains only zeros. Otherwise, something wrong, then we know we're gonna go back and check our work. Okay, so this is x, this is y, this is z, this is the right hand side. And then the second row tells us that I plus 1 times y equals to iz. So y equals to, sorry, I almost made the same error again, like last time. So it means I plus 1 times y plus iz equal to 0. So y is negative iz divided by I plus 1. Okay, we don't want to see the imaginary parts in the denominator. Let's multiply by the conjugate. Okay, so same thing, same terms, but flip the sign. Okay, that's the conjugate. Then minus I times I minus I squared is 1. Minus I times minus 1 plus I. And then the bottom, I squared minus 1, so it's minus 2. Okay. All right. So plug it into the first row. So minus x plus iy minus 3z equals 0. Okay, so x is then, move the x on the other side, we get iy minus 3z. iy, so y is 1 plus I over negative 2z minus 3z. Okay, so it's negative 1 half I squared, negative 1, so it cancels, become positive 1 half z minus 3z is minus half I z. Yes, and then 1 half minus 3 is minus 5 half z. Okay, so that's my v. X is minus 1 half minus 1 half I minus 5 half z. The y is minus 1 half minus I over 2z, and then this is z. Oh, so sorry, because of z, so it's 1, because we factor out the z outside. So let's pick z to be negative 2, because that will help us to get rid of a lot of negative. So then v is I plus 5, 1 plus I, and minus 2. So far, so good. Okay, so this is the eigenvector. Okay, let's check. Is this guy complex conjugates to the other eigenvector? Okay, keep in mind, I plus 5, 1 plus I minus 2. Oh, so here I have 2 and I minus 5 minus 1 plus I. That is because we picked the z to be different things. So if we pick the z to be 2, then we will have 2 at the bottom, and then all the others are negative. So then it will match, okay? So it will be 2 and then negative 1 minus I, negative 5 minus I. So they are complex conjugates of each other if we pick the z to be 2 as well here, okay? But it's okay. You know, this guy is still an eigenvector. Remember, a vector is an eigenvector, and then any scalar multiple of that vector is also an eigenvector. So in this problem, we find 3 roots. Okay, so 3 eigenvalues, 1 real and 2 complex, and usually the complex roots appear as complex conjugates. Okay, so that for each because we have 3 different eigenvalue, then for each of the eigenvalue we can find one eigenvector associated to it. Okay, and then the eigenvalue so the complex conjugate roots, we can find the complex conjugate eigenvectors. Okay, so that is the challenge example of 6.1. And then now we finished chapter 6. So yeah, chapter 6 we only covered this session, and that's quite enough for us. Next class we will talk about chapter 7, which is the last chapter of our whole course. We're gonna use the tools of eigenvalues, eigenvectors to solve systems of linear equations, differential equations. All right, see you. Bye.